from Dr. B.R. Ambedkar, NIT Jalandhar in year 2016. He is also a senior member of IEEE and served as Joint Secretary of IEEE Rajasthan subsection. Sir is a founding executive committee member and secretary of IEEE Delhi Section Antenna and Propagation Society Chapter Jaipur. Sir has also published research paper in very reputed international and national journal conferences, book and book chapter. Dr. Jayawardhan sir has organized 4 international conferences in association with Springer, elsewhere, IOP and IEEE. Sir has served technical program member also. We are honored to have you, sir. In addition to this, Dr. Jayawardhan sir is having a vast experience in IIT, in antenna, in super wideband, circular polarized antennas, terahertz antenna, metamaterial inspired antennas. Sir, we are honored to have you here. I request you to kindly please start the session. Thank you, sir.
Okay, thank you, Swati, for nice introduction. Very good morning to one and all present in this session. And I am sorry for this inconvenience and due to delay little bit and due to some technical glitch. So now without delaying further, I just start my presentation. So today I am just going to discuss about something about circular polarized antenna, what's going on in current scenario and what future aspect we are expecting in this field, especially from in Indian defense system and all these perspective. I will try to cover. These are some outlines of my presentation. So then little bit introduction about these antenna systems. What is antenna? Then little bit about polarizations. Then challenges in current scenario of circular polarized antenna, and then some designs that we have designed, and then summary and future trends about circular polarized antenna. How, what are the research objective? So as a day-to-day, the technology advancements are going on. So we need electrically small antenna so that we can form a structures that was integratable with a microwave integrated circuit. We can say that MMICs. So compactness with better system performance, and that should also be cost effective. So for that, we go for broadband and multiband CP antennas or metamaterial inspired antennas to achieve each objective. So before going in detail, just I will start from very basics that wireless communication systems. So as we know nowadays, everywhere we are dealing with data, transferring of informations in wirelessly manner. Wireless technology is used both in commercials, in defense, military, in every sector we are using. So what this wireless technology make enable or more efficient, we should have an efficient antenna. That was also one of the essential element of any wireless communication system. That antenna become integral and important part of almost any wireless communication system. So extensive efforts are currently underway to develop this multi-radio on a single module to address many wireless services or a wide frequency range. For this, the microstrip antenna are the most popular candidate for this multi-radio due to the attractive feature of microstrip antennas, like they have simple fading, planar structures. They are easily fabricated, low complexity, lightweight, mechanical robustness, and easily associated with monolithic microwave integrated circuit. So in this presentation, we mainly focus on the microstrip antenna. So traditional antenna optimizations tool show the original antenna design for each iterations. So we required lot of time to optimize these antenna designs, and they depend on the convergence criteria of the selected algorithm and time taken for each iterations. So as antenna are becoming more complex each day, so now people's using machine learning generated mathematical model for the physical antenna designs and performance fast and intelligent optimizations on these mathematical models. Now some of the EM simulators they also integrated with some machine learning based optimizations to design in complex structures or big structures that take more times when we simulate them with conventional EM simulators by based on FET or FEM methods. So the trained model allowed to run thousands of optimization iterations in a span of few seconds. Fast and intelligent antenna design optimization is possible with the use of machine learning and by using automatic process combining state-of-art mathematical method and predictive modeling, explore the design space of any system model smartly and efficiently. Digital antenna optimize now. What is basically antenna? So antenna is usually a metallic device for radiating or receiving radio waves. So we all know that we it convert electrical signal into electromagnetic waves and at the receiving end EM wave converted back to the electrical signal. So it is the end element for any wireless communication system. So designing effective antenna is important that completely realize your system, how efficiently that system works. Now need of antenna. So as we know this, from this figure, we can understand that in nowadays we consider our home appliances, we consider our office system, TV, weather forecast. Everywhere we need the wireless services that either be connected with some local services or some satellite services. So for that, we need an antenna to get communicated with all these wireless services. Now, for modern communication systems, we need an antenna which having compact size, high performance, high operating bandwidth, high gain, multi-band operations, mutual coupling reductions in antenna array, harmonic separations, and reconfigured operations. These basic specifications we required for any modern communication system where we want to design an antenna. So these are some basically typical antennas that we are using in our day-to-day life. Okay, like dish antenna, satellite antenna, cell phone antenna. Okay, antenna in our Wi-Fi access point, antenna we seen on the cell phone tower. So these are some different category. Here we are discussing more about this microstrip antenna, that how this microstrip edge antenna changed this era of this antenna designing. So what is microstrip antenna or printed antenna? That a this is basically an arbitrary shaped patch antenna that composed of a thin layer metal that is positions that is called your patch that is positions over the ground plane that both being etched on two sided of the substrate. So ground plane, then substrate, and then patch. So this is basic prototyping, or we can say that a basic structure of a microstrip patch antenna. These printed antenna are of the interest in wireless mobile satellite navigation, radar, portable terminal applications. So why they are popular? Because of their advantage of low cost, lightweight, planary structure, mechanical robustness, consistency on non-planar surface, and easily associated with MMICs. how we feed these antenna, how we excite these antenna or power them. So basically, microstrip antenna we can feed by four different techniques. This coplanar waveguide feed is somehow similar to this edge feed or microstrip line techniques. And we can say five technique or four techniques. Somewhere we see four techniques basically. So microstrip techniques, axial feed techniques, aperture couple technique, proximity couple technique, coplanar waveguide feed techniques. Now, what are the fundamental limitations in a conventional microstrip patch antenna or simple microstrip patch antenna? Because they provide similar, if we have not created much engineering on antenna structure. So basically, जो rectangular patch antenna, it provides you narrow bandwidth, lower gain, large ohmic losses in feed structures, excitation of surface wave, relatively low efficiency, high level of cross polarization radiation. They also provide spurious feed radiations that is basically created due to surface wave or strips, low efficiency, then low power handling capacity, and mismatch in the polarization. Wide bandwidth and circular polarizations are the two essential requirements for this modern communication systems to overcome all the limitations discussed in the previous slide. And these radiated wave from a patch antenna with single point feed are generally linearly polarized in nature. So matching the polarization in both the transmitter and receiver antenna is important in terms of decreasing transmission load. So for linear polarized antenna, it is very difficult to realize matching of the polarizations due to the multiple effects that we also discuss later. So for that, if we design an antenna which is circularly polarized, then it presents an attractive solution to achieve this polarization match, which allow for more flexibility in angle between transmitting and receiving antennas. And these two requirements may be easily achieved with rectangular plane geometry after minor modification. So basic idea for polarization is that polarization is basically geometrical orientation or the locus of the net electric field at particular coordinate space when time goes. This is general definition of polarizations, which can applicable for both linearly and circularly polarization. There is two parameters are associated with electric field. One is the magnitude of electric field and then direction on the basis of which different polarization states are defined. Now, the conditions for polarizations we check that we can decide by the basis of these two parameters of electric field only. What is the magnitude of the electric field generated by the particular structure of antenna, and then what is the directions or the phase of these electric field components. So the polarization of a radiated wave is the property of an EM wave that describing the time varying directions and relative magnitude of the electric field vector at a fixed location in space, and the sense in which it is traced as observed along the direction of propagation. So we have three classification of antenna based on the sense of the direction of propagation and magnitude: linear polarized antenna, circular polarized antenna, and elliptically polarized antenna. Basically, both linear and circular, we can say that the special case of the elliptical polarized antenna. So circular and linear are. So if there is only one electric field component, either EX or EY, or we can say horizontal electric field component or vertical electrical component, there is no another component, then we can say that that particular antenna is linearly polarized antenna, and based upon this magnitude of that field component EX or EY, we can say that either it is horizontally polarized or vertically polarized. Thus, if we design a structure such that it is able to create two electric field components, both electric field components are orthogonal to each other, then the sense of polarization, so the electric field, we can say that is circular polarization in the nature. So the conditions to accomplish this are if the electric field vector possesses two orthogonal linear components, and these two components have the same magnitude, and these two components must have a time phase difference of odd multiple of 90 degree. So these three characteristics must be met at all time. Then only we can say that our antenna is the circularly polarized antenna. If this phase difference is plus 90 or minus 90, then again it is sub-classification for circular polarization, that either it is the right-handed circular polarized or it is the left-handed circular polarized. So if the phase difference delta phi, that is phi y minus phi x, means phase angle of the vertical electric field component and horizontal electric field component, if it is the positive odd multiple of 90 degree, then we can say that the designed antenna provide the right-handed circular polarized. And if it is a minus 90 odd multiple of the 90 degree, then we can say that it is the left-handed circular polarized. But here we make sure that this Ex and Ey both should be the same. So ideally, the parameters we are checking to define an antenna is circular polarized or not, we are considering axial ratio of an antenna. That is basically ratio of Ex and Ey. Okay. So ideally, if antenna is perfectly circularly polarized, then we can say that axial ratio should be 1 in linear scale, and in dB we can say 0 dB. But for practical concern, we relax this criteria a little bit, and if an antenna providing axial ratio up to 3 dB, then we can say that that antenna is also your circularly polarized antenna. So here, the performance of circular polarized antenna is characterized by its axial ratio. Okay, so axial ratio is defined as ratio of major axis to the minor axis. So if both are same, that means the trace created by electric field, that is circle in nature. So with the use of circular polarized antenna, the system can tolerate changes in the polarization of the signal, and the changes in polarizations may be caused by reflectivity, absorptions, multipath, inclement weather, and line of sight problem. So these five parameters, they basically change the polarization of any EM wave that is transmitted or that is propagated in a free space. So conditions that most of the time can affect the polarization of transmitted wave. Hence, if the wave is circularly polarized, then it gives high probability of a successful link because they can transmit and receive signal in all plane. But our wave is not circularly polarized, and due to these effects, if the orientation of signal is changed, like I have transmitted linearly polarized signals, and due to this multipath the propagations or this mismatch in line of sight, if the orientation change by 45-degree inclinations or 90-degree inclinations, then at the receiving end, we are either receive limited power or we do not receive any signal. So for that, we focus on circular polarized antenna. So circular polarized antenna more popular when we talk about the satellite communications. Because from satellite, if we receive a signal, then it can go for the multiple factors and multiple, there is different layers in atmospheric layers, and then also the satellite is continuously moving in a particular orbit. So line of sight establishing is very difficult. Even we can say it is even not possible when we talk about the LEO satellites or MEO satellites. So for that, we go for the circular polarized antenna. Then these all issues or this line of sight problems can be overcome easily. Now, how we can find? So here two way I have defined by surface current or by the electric field. Means if the sense of rotations of electric field is counterclockwise, okay, and if the sense of rotation of surface current is clockwise, then it give you LSCP. If surface current rotation is anti-clockwise, then it give you RSCP. But in the case of electric field, it is reverse. If the sense of electric field vector rotation is anti-clockwise, then we can say it is LSCP. And if the sense of rotation of electric field is clockwise, then we can say it is RSCP. So here, this figure is for surface current. Well, we can see this is the clockwise, so it is LSCP. If this is anti-clockwise, it is RSCP. So this is about surface current distribution. And this figure is about the electric field vector rotations like left hand circular polarization or right hand circular polarization. So how we achieve? So by creating perturbation in the structure of page, we easily achieve the circular polarizations, but still it is not that easier. Positions, what is the size of this perturbation we should create, that is important. So we there is calculations, we have some mathematical expressions that define you to find out the positions and size of these perturbations we have created to achieve the RSCP and LSCP. There is three main techniques we are achieving based on the feeding of an antenna, that is single fed antenna, well-fed antenna, and synchronous subarray techniques. So we can use any one of them to realize CP antenna. So if we go for single feed antenna, then we have to create nearly degenerate eigenmodes to achieve the circular polarization. But here, single feed antenna provide as compact in size because only we have to need one exciting port, but they provide a small CPU bandwidth. But if you feed dual feed means we fed orthogonally one, then with delay lines or 90-degree hybrid phase shifters, then we achieve the circular polarization because we directly feed two electric two different directions. So automatically we get two electric field components, and that is our basic requirement. We should maintain the positions and everything should be like that. That magnitude of these two field components should be same. Then it give you CP, but again we can say that it take more space because of the additional equipments we required. We need some delay lines or hybrid phase shifters to feeding. So here we get broader CPU bandwidth, but we use more space. That is synchronous subarray techniques. It produces high quality CP due to cancellation effect, but again it requires more space. Here we are need for different antenna structures. They are excited with phase of 90 degree. So some typical example, conventional means basic single feed methods, like we if we feed diagonal positions. Okay, so this is the microstrip patch and this is the feed point. Okay, so here we are feeding on this diagonal. Okay, so if we feed on this diagonal positions, it give you LSCP. And if we feed on this diagonal positions, then it give you the RSCP. Both are circular polarized, but based on the feed positions where we are feeding it, it provide you the either LSCP or RSCP. Similarly, if we instead of feeding on diagonal positions, we can feed at center, but we are creating corner truncations. So this corner truncation can also give you LSCP and RSCP depending upon which corner we are truncated. Basically, they both structures are same. actually here in these structures, corners should be on these two edges. Okay, so it is by mistakenly I took same figure. Then another example for single feed circularly polarized microstrip antenna by creating additional stubs, by creating slots. Instead of corner truncations, we cut out slots from the corners. Or we can create a diagonal slot and fading on the center at 50 ohm positions. Okay. As we know, but that at edge of edge antenna impedance ideally infinity, and at the center point impedance of an antenna is 0. But practically, if we consider, then it is around 200 ohm at the edge. And if we move from this edge to this towards the center positions, then this impedance is decreasing. So we pick a point where we achieve the 50 ohm impedance and then we excite. So this is all about the calculation that what exactly positions we make this coaxial feed point so that we achieve the perfect impedance matching. So this is 50 ohm point. So we are exciting at this 50 ohm, and this because of this slot, diagonal slot, we are able to get the circular polarizations. So if we depending upon orientation, either I am cutting slot this way or in the opposite directions. If I rotate 90 degree, then it can also again change the sense of rotations, LSCP or the RSCP. And second is the dual feed method. So this second method is so to directly feed each of the two orthogonal mode with a microwave device that provides 90-degree phase difference. These 90-degree branch line hybrid or Wilkinson power dividers are the basic widely used two examples to achieve dual feed antenna. Another method reported in literature for getting circular polarized radiations is to feed square page at two adjacent edge to dual orthogonal field to excite two orthogonal modes using external power divider. And the feed at one edge excite TM10 mode and another generate TM01 mode. And because of this, we are able to get the circular polarization. So this is the Wilkinson power divider. This is the scattering matrix of this Wilkinson power divider. So we excite 6 feed signal here. There is lambda by 4 path difference is present in these two lines. So we are able to get 90-degree phase because of this 90 lambda by 4. This phase shift realized with delay line. Here we are additionally creating delay by adding additional lambda g by 4 phase difference. And in this also, if we feed here, then this will be transmitted like this. So it will also give you lambda g by 4 phase difference. And if we excite here, then this will be delayed by lambda g by 4 phase difference. So phase shift realized with 90-degree quadrature hybrid. This is branch line coupler and this is delay line and this is Wilkinson power divider. So any one of them we can use to design dual feed microstrip patch antenna. This gives us higher bandwidth than simple power divider, but it requires a load resistors because here we have two feed positions here and here. So either we can feed here, then we have to match this port. If we feeding here, then we have to match. Match means terminated with match impedance. That is your 50 ohm matching impedance. Then advantage of CP mic. So as already discussed that the orientation of transmitting and receiving an antenna need not necessarily be the same. So this allows the designer to have more freedom of design the transmission and reception systems. Applications, radar, GPS, mobile communication system, and satellite communications. So in mostly satellite communications required specifically CP antenna only. For CP applications, we go for the mobile communications, MIMO wireless systems. Okay, they have polarization losses due to misalignment, phasing issue, mitigation of multipath propagation, and it reduces effect of weather conditions and provide large signal coverage. These are some traditional circular polarized antenna. So, like uniform helical antennas, tapered helical antenna, spiral planar structures, they are providing broad bandwidth. These are the narrow band, simple uniform helical antenna. But if you go for tapered helical, then it will provide you broadband. If you go for the uniform helical, then it will give you single band CP frequency. But conventionally, they are used. Even we these antennas somewhere also used specifically on that satellite phones used by the defense system or police. Nowadays still they also using these on their vehicle. Now advanced modules also came with the integrated microstrip antennas for this effective communication of satellite, but still they are in the use. Now challenges in the CP realization. So first, it is very difficult to maintain amplitude and phase. Then two orthogonal components required more space than only one component of linear polarizations. In designing of omnidirectional, so for wide angle, it is difficult to maintain the orthogonality. Okay, what it is mean? Like if you design an antenna and that is allow you the CP, but it will provide you CP only for the narrow range, like 30-degree beam width or 40-degree beam width or 50-degree. But it is very difficult. We can design an omnidirectional antenna with a beam width of 180-degree or like omnidirectional CP antenna. Realization is very difficult, specifically if we talk about the if antenna type is a microstrip antenna. Pattern reconfigurability is also very difficult to maintain orthogonality of two components for all switched beam, because if we are designing a pattern reconfigurable and they are circularly polarized, then again it will create a cancelling effect will be applied, so pattern will getting cancelled. Again, fabrication of high frequency metasurfaces, then limited indigenous substrate technology and need for compact and high gain solutions. So these are some challenges we go for. They are in case of the designing perspectives, they are in the performance perspective. So now we go for some designs that we have implemented, me and some of my research colleagues. So I will discuss 3-4 designs here. So microstrip multipolarized quad band antenna. Then we go for broadband CP antenna, 12 band CP antenna. Then I will discuss one high frequency CP antenna that are operated for KU and K band applications. One polarization reconfigurable patch antenna for multi-band applications, and then one antenna will discuss that we can optimize with the help of machine learning applications. A simple GPS antenna we optimize with machine learning application. So this structure we have fabricated on RT dured 580 substrate materials having dielectric constant. This so here we have page is simple circular page with is excited with microstrip feed. But here in the ground plane we have created some changes. Okay, we can say that this is the partial ground modified defective ground we have created, and now because of these stubs and slots we have created in the ground plane, it will allow you to get different polarization state. So if we see the surface current distribution or this structure, then on the page it will not much varying on the different frequencies. But if we see the surface current variation on the ground plane, then The y-directed and x-directed surface current reach dense mainly on the L1 and W1 parasitic T stubs, and this is give you the resonant frequency at 2.6 GHz. This second resonance is due to these stubs, and they provide you the resonance at 4.6 GHz. These stubs we have created here, this will give you resonance at 5.65 GHz, and this stub is give you 7.6 GHz. So we have created multiple stubs. Each are responsible for providing resonant frequency. So it is quad band antenna that was operating at 2.6, 4.6, 5.6, and 7.6 gigahertz frequency. How to check the circular polarizations of the proposed antenna? We check the amplitude ratio EX or EY. So this is the EX EY, or we can say that axial ratio of this antenna, magnitude of EX and magnitude of EY, and phase difference. If you see, then magnitude is 1 other on this frequency at 5.9 gigahertz, and here at this 5.9 phase is also 90 degree. If we zoom view, this is the zoom view of this point. So if you go for the zoom view, we can see that it is at 5.9. We're getting the 90-degree phase, and magnitude is 1. So we can say that at this 5.9, it will provide you the circular polarization. So now it giving you CP, we get acceleration 1, but now what is the sense of polarization? It is left-handed or it is right-handed. So for that, we go for the vector surface current distribution, and we check either it is rotating clockwise or anti-clockwise directions if we move from 0, 90, 180, and 270 degree. So it is observed that different time instant, the same sense of polarization is right-handed if the direction at theta equals to 0 is in the anti-clockwise direction. Is 0, then it will be moving in anti-clockwise directions like this, then this, then this, and then this. It is anti-clockwise rotation, sense of rotation. It will provide you anti-clockwise. So we can say it is RSCP. Okay, so in one slide I discussed that if we talk about the surface current distribution, then if anti-clockwise, then RSCP, clockwise, then LSCP. But if we talk about the electric field distributions, then if rotation is anti-clockwise, then it is LSCP. If rotation is clockwise, then it is RSCP. So these are the measurement setup and fabricated prototypes, and we can see that there is quite adequate measurement. Results match with the simulated one. This is axial ratio. So it is quad band antenna, but it provides you circular polarization at one frequency, and at the frequency it provides you the linear polarization. 5.9, it provides you circular polarization. Remaining all other frequency, it provides you the linear polarization. Second is the broadband circular polarized antenna that is designed with slot and ground strips. So here, this is the proposed design configurations. This is your patch and this is your ground plane. Here in this ground planes, we have created some asymmetric L-shaped strips, spiral slots, stubs, and this I-shape patch we have designed. It is CPW fed. So these are the optimized parameters of this design. So it is compact in size. It is around 20 cross 20 mm, but it provides you the wide range of frequencies. Means it operating at 4.1 to 14.54 gigahertz frequency range. It is around 112% impedance bandwidth and 60% of the CP bandwidth. It is single band and broadband performance. These are the evolution stages. We move from this to this, how we reach up to the final optimized structure. and these are the optimized result. This is the surface current distribution. We have checked at two frequencies. Means basically it of providing CP from 6.47 to 12 gigahertz. But we have checked means for the presentation only at two frequencies. We are checking the surface current distributions, and this key mechanism of proposed antenna by surface current distribution at 8 gigahertz and 10.5 gigahertz with varying phase. So here 0, 90, 180, 270. If we see, then it is the clockwise sense of rotation, this way, this way. So if we check, it is the clockwise rotation. Sense of rotation is clockwise at both the frequency. So we can say that proposed antenna or this designed antenna provide the left-handed circular polarization at both the frequencies. This one is the fabricated prototype. It is fabricated on RO3003 substrate materials. We compared the result with CST, HFSS, as well as the measured result shown here. There is quite good measurement matching. We also check the SZ parameters gain for both HFSS, CST, and measurements. It provide the peak gain around 5.5 dBi. This is the 3D radiation pattern at different resonate frequencies. This is the two-dimensional radiation pattern. If we see here at this point, then we can see that it is radiating along the main lobe directions at phi 0 in both xz plane, theta 0 in both xz and yz planes. And we also check that there is good cross polarizations level. It is more than 15 in all the cases. So that can say the polarization purity of your antenna means there is more than 15 dB difference between the LSCP and RSCP. This cross pole level. So here the main components that are contributing in the circular polarization that are your inverted L strip and spiral slot that we have created, and that will allow you to generate the orthogonal field components, and these orthogonal field components are able to provide you the circular polarization. Then dual band circular polarized CPW fit is strip and slot loaded compact square slot antenna. So this is the some modified structures from that existing design, and these structures provide dual band resonance. Here, due to these spirals and this slot in the ground planes, it will create the orthogonality, and it will able to generate circular polarization. It is also small in size, 20 mm plus 20 mm, and it will operate in the frequency range from 3.56 to 10.10 gigahertz and 10.64 to 12.68. Means at dual band, one percentage bandwidth, if we talk, then 95.65 gig, 75 gig percent, and 17.49 in the upper band. And if we talk about the acceleration bandwidth, percentage bandwidth, then it is 74.81% and 11.57% acceleration bandwidth for both the bands. If we see that because of this slot we have created here, this slot provide you the variations in circular polarization. Means if you see antenna 5 and antenna 6 acceleration load, then by creating this slot means it will change the sense of rotation of the surface current or this antenna structures and provide you the wide band performance in CP. But it will not much changing in the impedance bandwidth, but it will help you to contribute in the circular polarization, achieving acceleration bandwidth. This is the surface current distribution. So we go for three different frequencies, two in the lower band, one at higher frequency band, and we can see that CP mechanism, and it the sense of rotation at all these frequency are clockwise direction. So this antenna is also provide left hand circular polarization. This is the measurement setup. This is fabricated and designed and measured. This measurement setup photograph shown here, it is from the GB Pant Engineering College, Delhi. So I have measured this structure, GB Pant Engineering. These are the result comparison between simulated, measured, as well as CST and HFSS. First simulated and optimized with two simulators and then measured. So there is quite a good adequacy measurements. Some mismatch is there, that is because of, if we talk about CST HFSS, then they both are using different methods to solve and domain. Then so that's why they will change in their meshing structures and solving the equations. For fabrications, there is some losses due to conductors, some material losses also be incorporated, so it will differ from the simulated one. Radiation pattern, if we see, then at two frequencies, we have shown the radiation pattern, XZ and YZ plane. This is 50 plane, this is 590 plane. Here, if we talk about the higher side, means at 12 gigahertz, then we can see that radiation pattern is not along the main lobe, that is at theta equals to 0. It is tilted, little bit tilted around 20 degree in theta, specifically in YZ plane. This is because the structure, means the slots we have created in this ground plane here at this point. So this acceleration will be provided only because of this slot, but because of these slots, the radiation pattern is slightly tilted from the main lobe and it is set at theta equals to 20 degree around. Its main lobe is not at theta 0, its main lobe is at around theta 20 degree. And here I will also shown the beam width of this antenna. So here if we check that both XZ and YZ plane at 5.5 and 12 gigahertz, then it will provide you the beam width 95 degree and 68.2 degree. So means we can say that it provides the CP for the wider beam also. And this table shown that where we are getting this phase. So at 5.5, my lobe is at theta 0, but at 12 gigahertz, this YZ plane at 590, this is shifted around 20 degree, theta 20 degree. It is shifted, and this shift is due to that slot we have created in the level of part of the ground plane. So it will disturb our radiation patterns. At lower frequency, demand for satellite and radar have been increasing. So due to the preoccupancy of the free spectrums below 10 gigahertz by various commercial and defense applications, researchers have started exploring the possibility of communication services higher frequencies, specifically greater than 10 gigahertz in KU, K, band, etc. We also go for the millimeter wave in different frequency spectrums, especially up to 60 gigahertz and terahertz also we are shifting. So communication system at this frequency band require antenna structure having high efficiency, wide bandwidth, high data rate, easy integrations and compatibility for development of compact communication device. All these requirements can easily be achieved by planar microstrip antenna structure that is designed on rigid or flexible substrate material. So a KU and K-band application based CP antenna that is designed with strip and slot loaded here present. So this is an antenna structures. Here we are using this modified epsilon sub structure will provide you the UW B frequency response means it provide the impedance bandwidth from 10.9 gigahertz to 28.8 gigahertz, and it provides the axial ratio in two bands, 12.8 to 19.05 and 28.85 to 28.5. So we can use this for the millimeter wave application, 5G application. This is the KU band. This is dual band, dual operations. Impedance bandwidth is complete entire band it is giving, but axial ratio giving in only to limited band only. This is millimeter wave band. This is your KU band application. And surface current distribution is the left hand circular polarizations. If the rotation of current is clockwise in the direction, it is fabricated prototypes and its measured results. Again, result is simulated. This is structured in both CST and HFSS, and compared with the measurement result, then there is good matching in axial ratio and impedance result. But if we see gain, then it is little bit differ between the CST and HFSS result, but measurement result is quite near to the CST result. Radiation pattern is quite disrupted at higher frequency. This is was designed on FR4 substrate, so huge losses we have faced at these frequencies. So radiation pattern is disrupted at higher frequency. Specifically, if we see 26 gigahertz, then this radiation pattern is almost disrupted, not able to differentiate. Their cross polarization level is very low, only around 10 dB only. Now, one reconfigurable structures I am presenting here. So that was basically not my design. So this design layout of the proposed polarization is a configurable ring shape patch antenna. Here, the simple ring shape design is presented, and four diodes they are using to make it reconfigurable. And simple ground structure, partial grounds they are using. So D1, D2, D3, D4. So by changing these four variations from D1, D2, D3, D4, we are able to achieve linear polarizations, right hand circular polarization, left hand circular polarizations. This design incorporate a ring shape radiator chosen for the symmetrical geometry, consistent angular performance. By controlling these diode switching, it enabling the antenna to operate across different frequency band. These are the some fundamental principle behind circular polarizations we can see. So surface current distribution is shown to frequency 6.6 and 12.2 gigahertz, and at due to the combination like D1, D3 on, D2, D4 off, then it provide you RSCP. If D1, D3 off and D2, D4 on, it provide you the LSCP. Similarly, at 12.2 gigahertz, it provides RSCP and LSCP by controlling the diode positions. And if all the diodes are in the off conditions, then it provides you the linear polarization. So if D1, D2, D3, D4, all diodes are on, all diodes are off, then it provides the linear polarization. If we use in the combinations, then we get LSCP and RSCP. Is fabricated and tested for all the frequencies. So there is a quite similarity between the simulated and measured result. One design where we are applying the machine learning, because nowadays this is quite popular topics. People are talking about antenna design optimization with the help of machine learning. So I have included one simple design based on optimizing an antenna with the help of machine learning. Means how machine learning help you to the optimize antenna and how fast it is with the conventional CST or the HFSS EM simulator. So here we have designed this is basic microstrip patch antenna, and these are the parameters that we use, like width of patch, length of patch, thickness of substrate, epsilon, dielectric constant, and operating frequencies. So when we design our antenna, then we are going to optimize these parameters only. Either we optimize VW, L, H, and ground plane dimensions also. So we give W, L, H, epsilon are the page input, and we get the optimized W, L, H, epsilon RF from this deep neural network. This deep neural network means any algorithm that is based on this neural network optimization algorithm or machine learning. So here we give them training data. Now question is from where we get this training data. So we get this training data from any EM simulators, either CST, HFSS, and then from this training data, algorithm learn the rules, and based on that rules, they send and optimize our structures accordingly. In order to apply machine learning in antenna designs, we go for the following step. First, by multiple simulations, electromagnetic characteristics of antenna are found out. Means first we design an antenna simply in our EM simulator. Okay. Then we apply the parametric sweep over there, and from that parametric sweep, we extract the results, means variation in some parameters, and depending upon that variation in parameter, what is the effect on S11, what is the effect on the axial ratio, what is the effect on the gain, and all other parameters. We take out these parameters, and we make a training set, different variations. As much data is there, more perfect results we will get. In these training data, we send it to any algorithm, a machine learning based algorithm, that is the optimization algorithm. Either that is based on the neural network or based on the some uh, general or nature inspired optimization algorithm. We send it to them. These characteristics are stored in a database and used as a data set for training a certain machine learning algorithm. And this data that give the closest result is designed by the algorithm after making predictions depending on the need of the designer. So what basically we required, based upon that, we train, optimize, and then this algorithm, this ML based algorithm provide you the predicted result. So these are the step flow of antenna design and optimization. So first, build parametric model. This parametric model we design in EM simulator only. So quantity to be optimized added as a solution request. Then we set up new study. We make a choose an ML algorithm, any KNN neural network, any optimization algorithm we took. There is thousands of algorithms proposed by the engineers or researchers working in this field. This parameterized EM model will be imported along with design variable. Now, these design variable design exploration and data collection be done. Then we train a model using machine learning, and based upon this model, they perform optimization on the ML train model. So this optimization will be extremely fast when we compare to the optimization using physical model. Physical model means there's model we are using based on the FEM, FDTD, FIT, all these computational methods. So simulation data with multiple variables, supervised data need for machine learning. Here we send machine learning with regressions, build a mathematical model that define the goal, return loss of the antenna as function of the geometry variable. It will create a mathematical models, S11, the page dimensions, and the speed position. and it will give you the optimization using mathematical model. So this algorithm, this was the already provided by the Altair software that we are using. Then optimization of a page antenna for GPS application. So optimize a square page antenna that is resonate sharply at 1.5 gigahertz for GPS application using machine learning. Here we have took a simple design that is GPS antenna and design for 1.5 gigahertz. So we have to optimize page size, feed position. There is four slots created. Their slots length, slots width, and slot to page edge distance. Means what is the position of these slots where we have put to them. Okay, they are not can't they cannot be placed on any arbitrary position. The position should be same, means fixed, so that it will able to operate on this 1.575 megahertz 1.575 gigahertz frequency or 1575 megahertz frequency. Then we set the goal as S11 should be less than minus 10 dB at this frequency. So we compare regular optimizations with such optimization using machine learning. If we see the chart here, then it will show that which parameter affect more on the S11. So if you see, means higher in the size, that means it having the more contribution. So page size will be the most dominating parameter that will help you to set your objective or goal at to resonate this antenna at 1575 megahertz frequency. Second is the slot length. Third parameter is long to page edge distance. Fourth is slot width, and fifth is feed position. So feed position has very limited. Feed position is basically help you for the matching of impedance only. Okay. If you perfectly match, that means power delivering is adequate to the antenna. Then these parameters are mainly decide that at which frequency our design antenna will operate. Based upon this table, this graph, we can choose the data set, prepare the data set, and means like page size will be more dominant parameters. So we get more data from page size, then slot length, and then we train our algorithm. So this is the fit automatically selected by training algorithm. So a trained model is generated from regression model using machine learning algorithm that is it automatically selected by training fast algorithm. If this is 3D surface representations means S11 and feed position, slot length, slot width, slot to page edge. This is the representation of the response surface from machine learning model. Now, analytically, if we see, then the time taken by the machine learning versus regular optimization algorithm is mentioned in this table. For data collections, 120, 160 seconds, because data collection will take more time. Because this data we collected from the conventional EM software only. So it will take his own time. Then train model, it will take 2 seconds, and optimization using train model 4 seconds. So total 168 seconds to be required when we design and optimize with the help of machine learning based optimization algorithm. But if we optimize same antenna for same parameters, then with regular optimization algorithm or in EM simulators, it will take more than 810 seconds. So if you see, it is around 5 times faster if you have done optimization with machine learning as compared to when we done optimization with our conventional EM simulator. So that's why if we go for the complex structures or more big structures, specifically when metamaterials and their array. Then to optimize that structures, if we get trained our data with machine learning based system, then we save our time. And here result comparison. So this is an optimized space antenna. Optimized, blue one is the optimized using machine learning, and green one is the regular optimization. So if you see, there is a little bit variation in the result, but it is near about similar. The deep regular optimization is more sharper result, but if you go for machine learning, it results is also nearly matched with the regular optimization point, but it save your time. So summary of this presentation. So in this presentation, we primarily focus of investigation in on design of circular polarized antenna to overcome the limitation of existing design. Brace printed antenna are designed, investigated, fabricated, and we have experimentally characterized them in terms of their S11, their axial ratio, radiation pattern, gain, efficiency, all the parameters. Then to analyze the performance of design printed antenna, CST Micro Studio HFSS we have used, and for measurement VNA and NOK chamber setup we have used. Significant of amount of investigation we mainly done on the CPW feed. We also discussed the microstrip feed antenna. CP antenna are essential for modern communication system. We see the need why we go for CP only. Now, what the future trends, what people's nowadays doing in this field? So, advancement in reconfigurable antenna, metamaterial based designs we can do to overcome that challenge in achieving wider bandwidth and higher gain, particularly for higher frequency in millimeter wave, 5G and satellite communication application. We can design antenna for these application. CP metasurface for terahertz and optical links. This is also a recent important topics. Many people are working on this topic also. AI optimized reconfigurable CP array. Then we design energy efficient CP for IoT and SATCOM applications. Low power variable designs. So these are some trends in CP antenna designs that nowadays people are doing. In manufacturing innovation, we go for the 3D printing CP antennas or flexible PCB or conformal CP arrays we can design. So this is all about my talk. This is the acknowledgement. So the measurement setup I have used for different structures. We go for the different labs at different time. So this is the acknowledgement. So this institute, they have their measurement setups and they help to make my work get published. Thank you. Now
Any
you can,
queries?
yes.
Sir, in the chat box, one question is there from the participant. In surface current distribution graph in RHCP, then at all the angles, the direction should be anti-clockwise or not?
Can you repeat, please?
In surface current distribution graph, if
Hmm.
RHCP is there, then at all the angles, the direction should be anti-clockwise.
If like our antenna operating more than one frequency, there is possibility that at some frequency it giving you RSCP and it giving you LSCP. So we have to check all the frequencies. Either their rotation is anti-clockwise, that means it is definitely RSCP, and if the surface current distribution is clockwise, then it is LSCP. But yes, in one design, if it operate on two frequencies or dual band operation or multi-band frequencies, then there is possibility that at some frequencies rotation is clockwise and some frequencies rotation is anti-clockwise. So accordingly, we have to decide.
Sir, is there any formula to design any structure? Participant is asking.
Formula for designing? No,
Yes.
basically we can, with the help of formula, we can design basic structures for single band operations, narrow frequency. To get wider bandwidth, we go for the optimization only. So for that, we are not mathematically define all these points, like we have created some slots. So to defining mathematically, it is difficult. So optimization is the way. By optimizing our structures and by taking the help of the literature, we can design. But yes, if we talk we want to achieve wider bandwidth and multi-band resonance, then formula is not sufficient for that.
Sir, is
The
there any
formula,
soft?
yes.
Okay. May I ask the next question, sir?
Yes, please.
Uh, wideband circular wideband wide beam circular polarized antenna for spectral monitoring applications. For this, which antenna is better, sir? I
Wide
think
beam and wide band.
I think the participant is trying to ask that it's written in the chat box, wide beam circular polarized antenna for spectral monitoring application. Which antenna is better, sir? Dear participant, can you please elaborate the question, Ramesh, sir?
Okay, I understand. Yes, for the spectrum monitoring application. For that, from microstrip, if we talk, then by using the microstrip antenna, it is little bit difficult to achieve wide band and wide beam simultaneously. Then we go for these spiral antennas, helical antennas. They are not planar structures, but yes, they will provide you with a wider beam. Yes, I think this is one of ISRO response project also. In nowadays, it is was floated by the SIC. They also demanding an antenna with wide band and wide beam. So for them, they required a antenna. They start from some megahertz to gigahertz frequency band. So for that, microstrip antennas are not that much suitable to operate on that wider range and with wider beam also. So for that, we can go for some structures that are based on the helical structures or that kind of the structure.
May I ask the next question?
Yes, please.
How can we do the regular optimization on HFSS or CST software? Do we need to manually change the dimensions?
There is two way. In CST HFSS for optimization, there is two options. One, we can go for the parametric sweep. Here we have to manually change the value. Second, there is one optimization option also, where we have to set target. Like we have four parameters L, W, S, T. Let's suppose anything. So we set the range like L I can change from 15 to 20, W I change to this, and then I put my target also there. Okay, I want S11 at this range of the frequency. My another parameter like you want to gain also. So S11 is sufficient for you, then only you can set your goal and then apply the optimization. But actually the systems basically we have as a student when we are working, then we do not have that high end performing system. So this optimization will hang your system because it will do the billions of the computations behind. That's why. So manual parametric variation is better approach where you can able to understand the effect also. Which parameter, by changing which parameter, what basically effect will be creating in your design and in results also.
Okay, sir. For wideband, when we use DGS, the radiation pattern goes to backside. Is there any solution?
Yes, solution is there, but again, every solution will come with some cost. Okay, so we go for DGS. Why? To get wider bandwidth or to achieve some feature in our antenna. Okay, but if you put some additional structures like some AMC reflector or some metamaterial structures backside along with your DGS structure, then yes, you are able to save the backside radiation, but again, your structure complexity is a little bit increased. But yes, it will help you to achieve the more gain and the directional radiation pattern. By adding some additional structures, either metamaterials or some AMC reflectors, you are able to remove this backside radiation. But yes, it will increase little bit complexity in your structure.
Okay, sir. Thank you, sir. Sir, one query is from my side also. Can I ask?
Yes, yeah, please.
Sir, which software you have used for the antenna optimization? Like you showed the last few slides for AI/ML, no?
Yes, yes.
So, in which platform you did, sir, that?
Actually, this is the Altair FEPO software.
Okay.
Yes, in that they have integrated system. Means they have provided they have two software. Means FEPO is for the EM simulations, and I just forgot the name. So you import data from FEPO2 directly in that software, and you can apply your ML optimizations there. But from CST services, you can also extract, like you take data, then use the MATLAB or Python, and you apply that data set in MATLAB or Python by selecting any appropriate optimization algorithm, and then you are able to do the optimization. But FEPO will give you integrated system, but CST services till now they do not able to directly linking with this machine learning optimization with EM optimization.
Okay, sir. Thank you, sir. Any more questions from the participants?
One questions,
Yes.
is, is it possible to improve pattern upside with adding other layer of metamaterials? Yes, it is possible. You can integrated these metamaterial structures in the ground plane only, means along with backside of the substrate, means your structures keep the planar only. You can put these pattern metamaterial structures in that backside along with your DGS structures, then you are also able to maintain upward direction radiation pattern, or we can say that Manlove radiation.
Okay, sir. So, thank you, Dr. Jayavardhan, sir. The session was very informative, and the beats of knowledge connected from the circular polarized antenna to the implementation of AI/ML in antenna is very commendable and informative, sir. Thank you very much, sir, and we are very much honored to have you here.
Thank you very much for inviting me. It will be great session for me also. I also learn many things. So thank you so much. Thank
Thank
you,
you, sir.
participant, for being passionate to listen me. Because it is a quite early morning. Everyone out to go. It is office time, but still many participants are there. So it is very nice. Thank you.
Thank you, sir. Dear participants, the next session will be from 11 a.m. sharp. So you are requested to kindly join by 10:30 in order to avoid any delay. Thank you.